Hello, everyone. Welcome back to the webinar. Today, we're very excited to have Pete Casazza with us, and he's speaking on undefinability of Tsirelson space. Pete?
Hello. I guess I'm required to acknowledge NSF. I owe them a lot. They've supported me for 45 years, and I never could have gotten where I was without it. So I can't resist putting this up. I may be the only person in the world who had a paper rejected by the Annals of Math because it was too deep. The referee's report said this paper is dense and impenetrable. So he rejected it. Okay, we're going to look at a central functional analysis problem. To what extent are the classical sequence spaces LP and C0 the building blocks of all Banach spaces? Unfortunately, I can't get this guy to go forward a page at a time. The problem for the 1960s, of course, was that every infinite dimensional Banach space contained an isomorphic copy of LP for some P or C0. Tsirelson gave the first example of a space not containing LP or C0. Gower said Tsirelson's space is probably the first truly non-classical Banach space. Tsirelson's construction, of course, was somewhat novel. The norm of the space is not defined by a single expression, but rather by an infinity process inspired by set theoretic forcing. So the space arises as a limit of approximating spaces. The most important thing about Tsirelson's space was actually Figel and Johnson. The original Tsirelson space was almost impossible to work with, to do anything deep. The space we actually call Tsirelson space now is the dual of the original Tsirelson space constructed by Figel and Johnson. They were absolute lifesavers because Tsirelson's original construction is actually geometric, while the Figel-Johnson construction is analytic. As Figel and Johnson point out in their paper, their construction makes the forcing approach employed by Tsirelson more easily visual. So this was absolutely critical. I think without Figel and Johnson, this space would never have gone where it went, because I started working at it right at the beginning. It was extremely difficult to do anything because it was basically abstract nonsense. The norm T is defined by an equation, but norm T appears actually on both sides of the equation. So at first sight, the definition almost appears to be circular. The actual construction due to Figel and Johnson is given by a fixed point argument. One has a sequence of norms on C00, the vector space of finitely supported sequences. Well, I said real numbers, whatever, complex numbers, such that the norms are increasing. And the norm of T then is defined as the limit over K of the norm of X sub K. And so we're working with all the ones for which this limit is finite. In contemporary Banach space theory, a norm that is constructed indirectly in this way is called an implicitly defined norm. This is in contrast with the classical norms, which are explicitly defined. That is, they're given by an expression that does not involve the object being defined. So they have an explicit, generally, formula right up front. So LP, of course, can be explicitly defined. It has an exact formula. For X equals the sum of AI EI. The norm of X sub P is the sum of the absolute value of AI to the P. So this is what we'll call an explicitly defined norm. However, it can also be implicitly defined if you want. You could define for K and N, the norm of X sub K is the sum from 1 to K of the absolute value of AI sub P to the 1 over P. Then, of course, the norms are increasing, and the norm of x sub p is the limit of the norm of x sub k. So theoretically, I could implicitly define LP, but of course, I don't want to. If I have an explicitly defined norm, this is to my big advantage. So one question we had in this job is, can you show that Tsirelson norm cannot be explicitly defined? Now, this is a little bit strange because I wrote an entire book on Tsirelson space, but somehow the problems that showed up here were something we never thought about. So they were all new for some reason. Oh, I should also throw in here, one of the biggest advances in Tsirelson to me is actually Bellinote's result, that the kind of unconditional version of Johnson's construction is equivalent and quite closely equivalent, I think within 4 of the original version. And we use that here also. So the question is, does every explicitly definable Banach space contain LP or C0? This problem was brought to the fore by W.T. Gowers in his 1994 International Congress of Mathematicians address, and later in 2009, when he proposed a polymath projection. And the problem was, the problem here is that part of the difficulty of the problem he was trying to pose, in that it involves making the meaning of explicitly definable actually precise. Odell pointed out, we're going to have to leave it to the logicians to precisely formulate this problem, since we're just not prepared to try to figure out what explicitly definable means. So part of the thing in our paper is we make it clear what explicitly definable is. Now, it's best if we're honest up front. These guys are, I'm not even sure what they are, model theorists, set theorists. That part of this paper is incredibly deep, and there's absolutely no way I could understand it very well. It would take a year for me to figure out what these guys are doing with model theory, set theory, etc. And it's actually so deep. I debated about leaving it out of this talk, because if you don't work in this area, this is going to make no sense whatsoever. Originally, I thought maybe I'd skip the definitions, and then when we go to using these, I could give you some intuitive notion of what they might mean, but I changed my mind and put it in. If this makes no sense whatsoever, don't worry about it, because you don't actually have to know this for what we're going to talk about. It's just worthwhile to have a rough idea of what the words mean. So in this paper, we're going to use ideas from model theory to introduce the concept of explicit definability of a metric structure. So in any given logic L over a class of metric structures, we'll prove in particular that if L is a compact logic for Banach space structures, C is the class of classical Banach spaces based on C00, then Tsirelson space is not explicitly definable from C in the logic L, which will then answer Gowers's question. More generally, we're going to prove that if X is a Banach space that is constructed from elements of C via the Figel-Johnson approach, i.e. the norm of X is the limit of an increasing sequence of norms of spaces in C, then X is not explicitly definable from C in the logic L. We'll also prove that once you have this class of non-explicitly definable spaces, if you use those to build others, they'll still not be definable. So we also prove that if C0 is a subclass of C such that every space in C0 contains LP or C0, then every space that is explicitly definable from C0 will contain LP or C0 as well. Okay, so the idea of explicitly definable will carry over to subclasses of what we're working with. So, like I said, I'm almost embarrassed by this for two reasons. Number one, it's extremely difficult if you've never seen it before. And number two, I'm not an expert on this at all. This, this is all really quite nasty for me. A logic L consists of the following items. It's a class of structures called the structures of L that is closed under isomorphisms, renamings, expansions by constants, and redux. For each multi-sorted vocabulary L, a set sent L called the L sentences of L, such that the sent L is in sent L prime when L is in L prime. A binary relation between the structures here and the sentences of L, such that if M is an L structure of script L and M is associated with phi, then phi has to be in sent L. It has an isomorphism property. If M is associated with phi and M is isomorphic to N, then N is associated to phi. And the reduct property, if L is an L prime, M is an L prime structure of L, phi is in sent L, M is associated to phi if and only if M increases to L models phi. So, like I said, I'm kind of sorry. If you don't work in this area, there's no way you're going to get much out of such a complicated definition. The first time you see it, I spent weeks and weeks and weeks just trying to figure out one sentence after another. So I'm not going to beat you up with too much of this. We'll just try to get out the words. Oh, I forgot. There's one more part of this, the renaming property. Suppose R is a mapping from L to L prime. We're calling it a renaming. Then for each sentence phi is sent L, there's a sentence phi R in sent L, such that if M is associated to phi, if and only if MR is associated to phi R. A logic for metric structures is a triple, K, sent, val. K is a class of metric structures that's closed under isomorphisms, renamings, and redux. Sent is a function that assigns to every vocabulary L a set L called the set of L sentences of L. And val is a functional relation called truth value, such that the following conditions hold. K is a class of metric structures that is closed under isomorphism, renamings, expansion by constants, and redux. Sent is a function that assigns to every multi-sorted vocabulary L a set sent L called the set of L sentences of L, and such that sent L is in sent L prime and L is in L prime. There's actually more to this definition. Val is a functional relation such that the following conditions hold. The relation val assigns to every pair phi M, where phi is an L sentence of L, M is an L structure in K, a real number val phi M in 0, 1, which is called the truth value of phi in M. It has the isomorphism property for logics for metric structures. If M and N are metrically isomorphic structures in K, then val phi M is val phi N for every L sentence. The reduct property again for logics for metric structures. If L is an L prime, phi is an L sentence of script L, and M is an L prime structure in K, then val phi M equals val phi M increasing to S. And finally, again, we have the renaming property for logics for metric structures. If rho maps L to L prime as a renaming, then for each L sentence phi of L, there's an L prime sentence phi rho, such that val phi M is equal to val phi rho M rho for every L structure M and K. And I think this is the last thing that we'll just throw out there. A logic for metric structures is compact or countably compact if for every vocabulary L, every uniform class of L structures is compact or countably compact in the L topology. So, you know, I almost feel like apologizing. If you don't work in this area, this is such abstract nonsense. It's just no way to grasp hardly any of it. Like I said, I spent weeks and weeks trying to read my own paper when they wrote it. So an example would be, let L be any logic for norm space structures. Let C be the closure in the L topology of the class of all structures of the form C0, norm L1, norm E0, E1, where C0 is a vector space of all finitely supported sequences. Norm L1 is the L1 norm. That is, it's the sum of the coefficients. The EIs are a basis. And this provides the main structure. And the final norm is a norm on C00. So this is something that makes a little more sense, right? This is looking something like Tsirelson space or something where in other words, this is showing this Tsirelson space, basically you can tell is actually one of these objects. E0, E1 is the standard basis of C00. Since any norm on C00 is Lipschitz with respect to the L1 norm, these are valid norm space structures. Oh, I must have copied and pasted this. See the appendix. I must have copied and pasted this out of the paper. For any two structures in C defined over M and N, define dMn as the quotient, the norm M over the norm N, where the norm of L1 is 1. The function d is continuous in both variables, hence we can define a formula phi xy for pairs of structures in C by phi xy is the log of dxy over 1 plus the log of dxy. Okay, so we made it through the painful. Let's look at Tsirelson space to see that it's going to satisfy this problem of Gowers. If E and F are subsets of N, we'll write E is less than or equal to F if the maximum of E is smaller than the minimum of F. E is strictly less than F if the maximum of E, whoops, this is a misprint, is strictly less than minimum F. And we'll write N is less than or equal to E in place of the set N is less than or equal to E. Again, C0 is a set of all finite real sequences, and Tj is the canonical basis of C00. For X in the sum of for X, it looks like the sum of A and Tn in C00, and any subset of the natural numbers, we'll write E of X as the summation over N of A sub N, T sub N. That is, we'll pull out the terms of this series whose subscripts come out of E. I must have just copied that page over. So for Tsirelson space, if X is in C00 and X is the sum of A and Tn, we'll define a sequence of norms indirectly by the 0th norm is the max of the coefficients. And for any k, the k plus first norm is the maximum between the kth norm and the maximum of 1/2 the sum of the norm of EI of X sub k as I goes from 1 to M, and the EIs are bigger than M. This is absolutely critical here, that the EIs are bigger than M, and they're increasing to the right. If it was then, oops, something went crazy here. I must have hit something. There we go. It follows that the norm of xk is smaller than the norm of xk plus 1, which is also smaller than the L1 norm. So norm xk is 1 Lipschitz with respect to the L1 norm, so we had a valid norm structure in here someplace. The Tsirelson norm is the limit as k goes to infinity of the norm of x sub k. This, of course, is the Fiegel-Johnson. Oh, I put it up here. This is the Fiegel-Johnson Tsirelson norm. Tsirelson space is the completion of this. The important intuitive thing here is you never ever actually have to compute the norm of t. Since it's the limit of the norm of x sub k, if you know the norm of x taken over all the k's, that's good enough. Whatever inequality you prove is going to be good for norm t also. So we'll let L be the class of all structures such that the norm completion of M contains C0 or LP. For M and N and L, again, we're going to define DMN as the sup of the norm of X sub M over the norm of X sub N, where the L1 norm is 1. We need to prove the Tsirelson space is not explicitly definable over L. So we need to prove somehow that the sup over I less than J of phi norm I comma phi norm J is not equal to the nth. So what is the problem here? And let me just point this out. The first thing we have to know, which is at least intuitively obvious and abstractly obtainable from what we know about Tsirelson, is we need to know that the Tsirelson norm is not actually equivalent to one of the kth norms. Now, this is sort of intuitively obvious, and you can drag it out of a lot of theorems. But it turns out we actually need the value of k for what we're doing. And the reason, of course, is that the norm of x sub k is an explicitly definable norm. So if the norm of t is equivalent to the norm of k, then Tsirelson would be explicitly definable. And we're trying to prove it's not explicitly definable. Then the Tsirelson space would be explicitly definable, and we're claiming it's not. So we need to show that this, in fact, is not true. It's not possible for the norm of t to be equivalent to the norm of k. Unfortunately, this uses up about 7 pages of this argument, because it turns out we need a little more than this. We actually need to know the value of this big K, and it's extremely difficult to compute. So we'll look at the beginning of the induction process, and we'll just leave it there. So we're going to fix an n, and we're going to look at a vector, the sum from n plus 1 to n of 1 over n. Then the 0th norm of this vector is 1 over n. But the 1 norm is a half. So this is the first time we're passing from k to k plus 1. And we can see that the increase, that there's x's for which passing from, quote, k to k plus 1 is a huge jump. At least from 0 to 1. So there, in this case, there's no k for which the norm of x1 is equivalent to the norm of x0. So that basically is starting an induction proof. If we look at one extra case, suppose we choose n1 less than 2n1, n2 less than 2n2, etc. We'll let x be the vectors we just constructed one after another, forming one after another. The 0th norm then is, of course, 1 over n1. It's just the sup of the coefficient. I didn't put the ti's in here. This is not supposed to be the sum of 1 over n1. It's supposed to be the sum of 1 over n1 t sub m, the sum of 1 over n2 t sub m. These are supposed to be vectors in the Tsirelson space. Then the 0th norm, of course, is the smallest coefficient, the largest coefficient, which is 1 over n1. The 1 norm can be computed, and it actually takes work, unfortunately. It shouldn't, it should be trivial. You could just take 1/2 the sum of each of these norms. Shoot. Oh, yeah. The one norm is just 1/2 the sum like it was before. This is 1/2. But we're working with this. And again, I'm sorry, I left the TMs off of these guys up here. But if you take the 2 norm, you'll actually look at 1/2 the sum of each of these terms to the 1 norm, but the sum of each of these terms to the 1 norm is actually 1, and there's n1 of them. So this is 1/4 of n1. So we have a set of vectors for which the 1 norm is 1/2, and the 2 norm is at least n1 over 4, where n1 is arbitrary. So again, we are seeing that the 1 norm is not equivalent to the 2 norm. So then basically, so there's no k for which the 2 norm is smaller than k times the 1 norm for every x. So the main thing we're going to show by induction is if you look at the kth norm in the definition of Tsirelson, for every k and every n, there's vectors xi, I goes from 1 to n. X equals the sum of xi. I didn't say this here. Well, that's okay. So for every k and every n, we can find vectors xi so that the kth norm of xi is 1/2. The kth norm of the sum of xi is actually 1. And this is what we saw earlier. If the coefficients of the vectors as you move to the right get tinier and tinier compared to the previous, then this norm of the sum isn't much better than the norm of each vector. And most importantly, the norm of x of k plus 1 is at least n over 4. So this is saying, in other words, again, the kth norm and the k plus first norm are actually not equivalent. Now, we actually had to prove more. This is not quite so bad. And I thought I put it in here, but I may not have proved the more. I guess I did not, but I should have. Along the way, we actually proved that the k plus first norm, we gave the perfect upper bound for the k plus first norm. The k plus first norm, of course, is not smaller than the kth norm, but it turns out the k plus first norm is smaller than the kth norm plus 1 divided by 2 to the k times the L1 norm. And this is an actually perfect inequality. I'm sorry I didn't put it in here. I should have. I must have been tired or something. So the k plus first norm in Tsirelson is always smaller than the kth norm plus 1 over 2 to the k times the L1 norm. And this inequality is actually critical to proving all of this stuff that we're doing. The method used to construct T has been continuously generalized, as you know, to answer many other problems. Slumprex arbitrarily distributable space. The Gowers-Murray hereditarily indecomposable space. The Odell-Schlumprecht solution to the distortion problem. Gowers' solution to the hyperplane problem. Gowers' space, which does not contain C0LP or a reflexive subspace. The Agiros-Hayden solution to the scalar plus compact problem. That may be all. We actually prove a similar result in here for Schlumprecht space, and it's unfortunately a ton more complicated. And again, we proved there's a k and an n. For every k and n, there's a vector x in Schlumprecht space satisfying the kth norm is 1, the k plus first norm is bigger than n. And there's also a, which I don't know why I didn't put these in here because they were separate theorems. There's also a relationship to the L1 norm, k plus 1 versus k versus the L1 norm. And this relationship is actually critical to everything we're doing here. So suppose L is a logic for a norm space structures and I is the class of structures based on C00. Let phi xy be a formula for pairs of structures in C00. And we're not saying anything about what the formula is. Let norm x of star be a norm, any norm on C00. If the norm of x sub I is a family of norms, we'll say that that little t shouldn't, well, t p sub phi of xi determines the norm star uniquely if for every Alter filter on I, the limit type t is realized and the norm is its unique realization. However, whenever M triple norm realizes t, we must have that triple norm of x is equivalent to the norm of x star for every x in C0. We'll say the norm star is uniquely determined by its phi type if there exists a family of norms on I such that t p sub phi of xi norm of sub I determines norm star uniquely. So explicitly definable for us, let X be a compact logic for norm space structures and let I be the class of all structures such that the norm completion of C00 contains LP of C0. There exists a formula phi such that norm T is uniquely determinable by its phi type over I. The phi type of norm T over I is not explicitly definable. Yeah, so this is getting back to Tsirelson. We want the norm that we're working with to be uniquely determined by its phi type, but we also need that this norm is not explicitly definable, that it really does behave like Tsirelson. So the point here is there's a lot of counterexamples to Gowers' theorem. It's just that T is one of the norms that we can explicitly show that it doesn't satisfy these conditions. So it's a counterexample to, well, I don't know if you call it a counterexample. It answers Gowers' problem. But there's a lot of other spaces that probably do this. And like I said, we also showed Slumperk space does. My guess is most of the other spaces I mentioned above, Gowers-Murray, Slumperk-Odell, all of these are derived from the ideas of Tsirelson, and they're probably all examples of Gowers' question. If L is a compact logic for norm space structures and norms of star is a norm on C0, given by the norms of star as a soup of the norms sub K, where these norms are increasing, let I be the class of structures based on C0 such that C0L1, C0LK for all K and N, that these are all in I. And one of the following conditions must hold. There's a K in N such that the norm star is equivalent to norm K, right? So this brings us back to, I took a few minutes just to discuss this in Tsirelson, that we need to know that the norm T is not equivalent to norm K for one of the Ks. So in the general setting, we in a sense have the same problem. We have an increasing sequence of norms that's going to define a unique norm. And we need to know that the norm we're getting out of this is not equivalent to K, or looked at a different way, that one of two things has to happen. Either this norm is equivalent to the K norm, or it has to solve Gowers' problem. The second possibility is there's a formula phi such that norm star is uniquely determined by its phi type over T, and the phi type of this norm over I is not explicitly definable. So this is saying basically if you have a sequence of increasing norms and you have this norm sub K, and the limit of these norms gives you a Banach space, then one of two things will happen. Either this space, the norm, is equivalent to one of the kth norms for some k, or it's an answer to Gowers' question. That is, the norm star is uniquely determined by its phi type, and the phi type is not explicitly definable. Oh, well, it's a lot. God, that was only like 37 minutes. Apparently, I haven't lectured so long. I forgot how long it takes to give a talk. This is Chase. Chase Bunny. He's as cute as they get. Anyway, I apologize because if I had realized I had another, what would I have had, 10 minutes, maybe I could have explained this more clearly. But like I said, the model theory part of this is serious in their area even. And for those of us who are outside the area, it's really extremely difficult to be able to follow this, to follow these definitions because they're extremely complicated and they have unending parts to them. But basically, I guess what you can get out of this is Tsirelson is not explicitly definable. There's no sort of way to find any kind of a logic system or a metric system or an anything system for which you can give an explicitly definable norm for Tsirelson. And that's critical for this problem of Gowers. So anyway, I guess I apologize for not being more careful. I didn't realize, I thought, anyway, I actually haven't lectured, I think, in a year. Actually, maybe not in 2 or 3 years since I started having operations. So anyway, that's our situation. Anybody want to know something? And don't ask me anything about the logic here.
All right, thank you, Pete. Well,
yeah, I have a question.
Go ahead, please.
Okay, Pete, can you say something about the positive result, that if you have an explicitly definable space, then it must contain an LP or C0?
You know, that's, I don't know how to say this exactly. These guys wanted this to be as abstract as is humanly possible. If you actually go to a concrete setting, you know, an exact example of what they're trying to define completely abstractly, so it covers everything. If you go to just one concrete example of that, you can actually see how Tsirelson space works and how other things don't work. If you stick with their definition, I don't understand anything about how to prove these things.
One example would be fine, if you could say.
Yeah, unfortunately, I don't have one off the top of my head that could be done in anything without a blackboard and something. But it's, let me see if I can find it. If you go to, there's an example in here, and you can, I don't know where I put the example. It's here someplace. The example is sort of explicit in a certain sense. Oh, it must be down past here. You can actually use this example to try to do something that makes sense. Here it is. Let L be any logic. Well, you know, what does L be any logic mean? I don't know all the logics. But if you went to this example and actually did it concretely, that is, don't look at, quote, any logic, try to pick some actual logic that the rest of us know. let C be the closure in the L topology. This is a mess, even for an exact example. Then you can actually get sort of a vaguely understandable sort of example of what these guys are doing. And if they had done it this way, you would have gotten one counterexample to Gower's, well, I say counterexample, one answer to Gower's that might be reasonable to understand. But these guys are absolutely determined that they were going to give an answer for, you know, whatever, all possible logics, all possible topologies, all possible everything. Like I said, I don't even know, I'm not even sure I know one exact logic, hardly. But way back when we started, it seems to me I tried to do this with a particular logic. But again, it was so long ago. We started this, I think, in December, maybe January, December. I don't even remember what I worked on at the time, unfortunately. But at least I believe that if you were to pick some logic that we understand, you could actually see an example of this, which is makes some kind of sense. The way we've done it, for those of us outside of logic, it doesn't make any sense whatsoever. I don't even know what a class of logics are. You know, all this stuff they're defining here. You know, we have if you go back here, we have a logic for metric structures. I don't even know what that means, a logic for metric structures. We have L sentences, truth values. And there's other things in here. We have isomorphism, renamings, expansions by constants. Oh, here, that, renamings. I never did figure out what renaming. What does it mean to rename something inside of a logic? There's whole parts of this I just don't understand anything about.
It's actually pretty simple. You just replace a name. You replace the name of a function by some other name.
Oh, okay.
All functions f are now called g.
Okay. Okay.
You're just changing the vocabulary instead of having f's.
Thank you. Can you answer Bill's question? I can't. I just don't understand this.
Is there use of Moret-Krivine in getting these copies of LP or C0? Doesn't it have something to do with these definable types being stable in some sense?
Yeah, that's right. It does.
I think it comes from the notion of definability that is pulled in from all theory actually has stability as a consequence. And then you can just apply Moret-Krivine.
But these guys are really quite smart. I mean, these guys in model theory, these are some smart guys right there.
So, but this is interesting. So the Moret-Krivine stability theory comes up, but that's an isometric theory.
Yeah, no, the idea is, no, it doesn't, you don't use it. It doesn't come up any place as such.
Okay, it doesn't come up as a theorem quoting mechanism, but in the approach, you mean?
Yeah.
Building types, I see. Yeah.
So from
it's actually true that the Moret-Krivine theorem or ideas came from model theory, and I hope, Pete, that you had a chance to send this to Krivine in particular, who should be very interested by the whole thing. He is still around and well, as far as I can tell, so it would be good to poll him about this result. Did you communicate with him at any point?
No, you know, it's on the archive, so that's, I just put it on the archive and let it go. The new paper will be on the archive in about a week, maybe. 2 weeks, let's say 2 weeks.
Pete, I also had a question about what explicitly definable could mean, which is, as you rightly said, quite complicated to grasp. If you try this type of definition, which is independent from what you said, say that a norm on C00 is explicit if there is some computable function f. I would need also to say what computable means, but it's a different story. A computable function f, so that given a vector v and some epsilon, I can compute the norm of v up to epsilon in less than f of v epsilon steps. Let me call that definable, if you wish. Is there something you can say about Tsirelson space for that definition?
I doubt it. At least offhand, I don't know what I would say. Right. See, like I said.
Another thing, will you continue to insist on norms, or semi-norms will also be allowed?
This is what we worked on. I actually haven't given any thought to, a generalization or something else. From my point of view, this is the logic here is so abstract that it's hard for me to really figure out what the heck we're doing. I actually think of this more like Tsirelson. It is, you're in a situation where you have a set of K norms increasing. They produce a norm, and it's not equivalent to any of the K norms, and that's most of the properties of Tsirelson space that make this all work. And so, somewhat, those are undefinable spaces. At least, from my mind, so that I can kind of hold on to it. For them, this is just like triviality, but for my mind to try to hold on to it, I actually think of it as Tsirelson, that if you have a sequence of increasing norms and they define a Banach space, and the norm of the space can't be equivalent to any one of them, then this should be undefinable.
Okay, thank you, Pete.
But the model theory part aside, that I don't understand either. But from Banach space point of view, what property you think that the Tsirelson space it makes it not explicitly definable? Is that just this norm, that increasing norm, the property? That looks very weak, because when these discussions were happening in the Gowers blog, things were people were looking into much deeper things. So this looks a very simple sort of, and I'm not sure if it's. Is that it? Is that the only thing you're using? That the xk plus 1 norm is greater than xk in a large function?
It's a lot more complicated technically than I said, because when we started out, I mentioned that LP has an explicitly definable norm and an implicitly definable norm. So there is a technical issue here which we had to get past. That is, the Tsirelson norm is not explicitly definable using those norm xk's. You have to answer the question, is there a formula someplace else so that you can write down the Tsirelson norm as f of this, or the sum of these, or something?
How about this? Does the complexity of Schreier sets comes into the picture that we use?
I didn't use anything like that, so I don't know.
Well, then, for example, if you use like Zafiri spaces, they are also like that, but then you don't use the Schreier set. So will you call those implicitly defined? I
really don't know. Like I said, I don't even 100% understand their definition. So I'm mostly working off my intuition, which is not accurate. But at least it gives me something to hold on to. Otherwise, this is so abstract, I have no idea at all what's going on.
Let me ask you one other question about this explicitly definable. If you have an explicitly definable norm and a norm equivalent to it, is that equivalent norm also explicitly definable?
Yeah, under what they're doing, yeah. even though the equivalent, okay, you may have a norm that has an exact formula, and you have an equivalent norm which maybe doesn't have an exact formula, is still considered explicitly definable. Simply because their definition essentially implies if two norms are equivalent, one is explicitly definable, the other one is by definition.
But wouldn't that imply that an implicitly defined Banach space will never embed into explicitly defined one,
Right.
which is of course nonsense, right? Oh, so this, so you're not saying anything about the subspaces thing, okay. All right, any other questions? So I'm exhausted.
Thank you very much, everybody. Nice to see you again. It's been a long time.
Yeah, thanks,
Yeah.
Pete.
Thank you. Gidon had a comment. I'd like to ask him to say something.
Yeah, I don't know if all of you know, but Tsirelson passed away this last January.
I didn't know. That's too bad. I got many years of my life out of him. And of course, this was a major advance for Banach space theory at the time, and the consequences, as I mentioned in the talk, are unbelievable. The number of problems that came out of the idea. I mean, the number of famous results that came out of the idea.
Yeah.
Well, apparently he had such ideas in different areas. I think computer science and other places also very influential things that he did. Yeah, I heard about that, unfortunately. There was a lot of discussions online in different communities about it.
Well, everybody stay safe and stay away from the virus.
Yeah, thank you so much, Pete, for giving the talk. We enjoyed it. Thanks a lot.
Thank you.
Thank you.
And take care. Stay safe.
Yeah, thank you for
we usually stay, to chat if you like to stay around.
Yeah, I'm not going anyplace.
Okay, yeah, sure. Let me stop sharing your screen so you can see more people. All right, there you go.